fear has forced me to come back and think of how these topics are relevant to the study of spectral theory problems for Schrödinger operators. So I'm going to describe some models of discrete Schrödinger operators with potentials that are dynamically defined. These are Schrödinger operators on the integer lattice, where the potential is defined by sampling a function along the orbits of an ergodic transformation. In other words, we have an ergodic system that's a phase space, a sigma algebra, a probability measure, and an ergodic map on X. We have an observable, which is just a measure of bounded function on the phase space. And then the potential function is defined by sampling this function along the orbits of the transformation. There is a recent preprint survey of David Amanik talking about such models. It was very useful to me to organize my thoughts for this talk. So I'm going to give you several examples of such dynamically defined Schrödinger operators. So to do that, I have to indicate the base ergodic system, and I have to say something about the sampling function. The first example, we call it the quasi-periodic model, is just a torus translation on a torus of one or several variables by an ergodic translation vector or point. And I have to say that in all our work, we have to assume that this translation is not just rationally independent, but it also satisfies a Diophantine condition. And the sampling function in general is assumed to be analytic. You have already seen last week, and you'll see much more of this next week during the workshop, that people work on these types of models with functions, with sampling functions that are not necessarily analytic, but we do assume analyticity. And I wanted to mention there is another survey that just came out of Chris Marks at Svetlana, where this model is discussed in detail. Another model that I'll mention is the random or IID or the Anderson model. So in this case, the ergodic system is the full Bernoulli shift, which consists of the following. So we have a state space or a set of symbols with a probability measure. So this can be any compact set space. And then the phase space is going to be the set of all sequences of symbols with the product probability. And the transformation here is the forward shift. And the sampling function, it's a function which has a higher degree of regularity. It's locally constant, or it depends only on one coordinate. So depending on your symbols, you could take the sampling function to just get the 0th coordinate of the vector, or you could take a function from the state space to R, which is measurable, and evaluate that function at the 0th coordinate. And then the potential function at each side of the lattice will give the nth entry or coordinate of the sequence. So in other words, what you get through this process is the potential is any IID random process. Okay. The next model that I want to briefly discuss is the Markov system model. This can be defined in a much greater generality, but for convenience, I'm going to describe a much simpler model where the space is a subshift of finite type and equipped with a Markov measure. So I'll quickly remind you what this is. So we choose the state space to be a finite set, and then let M be an adjacency matrix. So this is a matrix whose entries are all 0 and 1. you can think of this as simply encoding a finite graph whose vertices are the states, and the adjacency matrix tells you if there is an edge from I to j. So there is one if the entry ij of the matrix is 1. Okay, and then the phase space describes, it's the set of all sequences. You can think of it as all the doubly infinite admissible paths through this graph, right? So if you are at this point, you can go to J if and only if the adjacency matrix is 1 at the entry ij. Okay, so this is the phase space. It turns out to be invariant. It's clearly invariant under the shift, so you can restrict the Bernoulli shift to it. So this is our space. We have the phase space, we have the transformation. Now we need a probability measure on it. And this is where things become interesting. So we are going to define a Markov measure on this subshift space. And we define it this way. First, we take a transition probability matrix. What this does is it encodes the probability to transition from the edge I to the edge j. So this is going to be a number, Pij. Okay, so this matrix is assumed to be stochastic and compatible to M. What it means to be compatible to M is that if the probability to transition from I to j is positive, then there should be an edge from I to j. So that would mean that Mij is 1. Okay, and then what we do, we put an initial probability on the state space, and then we evolve it. So the initial probability is described by a probability vector P1, Pn. And then we want to put the probability on the space of sequences. So first, it's enough to describe it on the set of cylinders that generates the sigma algebra. A cylinder is the event that x naught is I naught, x1 is I1, xm minus 1 is Im minus 1, where I0, I1, Im minus 1 are some states. Okay, so what's the probability of this event to happen is going to be the probability to start at I naught, and then to transition from I naught to I1, to transition from I1 to I2, and all the way to the last. Okay, so there is a unique probability measure on it should be xm here, on this subshift with this property, and this is called the Markov measure. Okay, so this is our ergodic system, and then we define a sampling function there, and we can define it in different ways. One is to consider a locally constant one, so one that depends on the zeroth coordinate, like in the IID case. So what we get there, the potential will be a Markov, given by a Markov process. Or we can make things more interesting and perhaps more to encode better the fact that the underlying space is a Markov dynamical system. So for a Markov process, the events are not independent from each other, but given the present, the future is independent of the past. So what we do, we can take the sampling function to depend on two consecutive states of the system. So the present and the immediate future. And then the potential is going to be at each side n depends on the current and the next state of the system. Okay, so these are, there are more examples of dynamically defined potentials. You can take the skew translation, some people call it a skew shift, where you have a translation in one, this is on the torus of dimension 2, you have a translation in one coordinate and then the sum of the variables in the other. We can take expanding maps, for instance, the doubling map on the torus. You can take a hyperbolic total automorphism, for instance, the cat map on the torus of dimension 2, and so on. These are examples that we are interested in. And now going back to the Schrödinger operator and the Schrödinger equation defined this way. So this is a second order finite differences equation, and you can solve it by turning it into a first order finite differences equations. And what you get out of this, when you solve this formally, you get a transfer matrix. Transfer matrices are have a special form. They are defined starting with a matrix valued function, and then considering products of this matrix valued function evaluated at the orbits of the base transform. Okay, so this takes us to the next relevant concept, which is the concept of cocycle or Schrödinger cocycle, which is this function here. So given the dynamically defined Schrödinger operator, the associated Schrödinger equation, we have a map from the phase space to the space of 2 by 2 matrices defined this way. This defines a new dynamical system, a skew product map, and its iterates are the iterates of T and the iterates of this map, which are products of matrices where the cocycle is sampled at x, at the T of x, and so on, Tn minus n of x. So these are the orbits of the base transform. So these are the transfer matrices. Okay. Now we can define the Lyapunov exponent, whose existence is due to Kingsman's ergodic theorem. So the maximum Lyapunov exponent is a number associated to a cocycle. The cocycle depends on the energy. So I use this notation L. This stands for Lyapunov exponent of the cocycle, but since the energy determines the cocycle, we also use this notation L of E. Is the almost sure limit of these pointwise quantities, and is also the average, the limit of the space averages. And we are going to give these space averages a name. We call them finite scale Lyapunov exponents because they converge to the Lyapunov exponent, to the infinite scale quantity. Okay. So let me describe to you now what the goal of our work is. So we have a base ergodic system, we have a sampling function, we have the corresponding Schrödinger operator and the corresponding maximum Lyapunov exponent. And the goal is to talk about the continuity properties of this object as a function of various input data, either individually or jointly in different input data. And what input data could consider? Well, the energy parameter, of course, could be the sampling function that varies, could be the base dynamic, or the probability measure here. And considering all of these does not make sense for every single model. Of course, it's interesting, for instance, when it comes to the Bernoulli shift to perturb the probability measure and see if the Lyapunov exponent is stable there. When it comes to the quasi-periodic cocycles, it's interesting to perturb the transformation. In other words, to see if the cocycle, if the Lyapunov exponent is continuous in the frequency as well. Okay, and the related problem is that of establishing a modulus of continuity of the Lyapunov exponent under appropriate assumptions. And I will not go into why these things are interesting for or applicable to mathematical physics. It's well known. I will just say that continuity properties of the Lyapunov exponents are intimately related to similar properties for the integrated density of states. This is known to be continuous and in fact log-Hölder continuous in a very general setting. We'd like to know if the modulus of continuity of the integrated density of states can be stronger than this. And there is a way to relate the two quantities via Thouless formula or via the Hilbert transform. And this is a non-trivial statement that the Hilbert transform preserves certain moduli of continuity. So if you know the modulus of continuity of the Lyapunov exponent, say, and that modulus of continuity has certain properties, then this is true also for the integrated density of states. And that's the case, for instance, with Hölder continuity, weak Hölder continuity, and possibly for this too. This I have not checked. But anyway, this is a non-trivial statement whose proof you can find in this paper of Gorsin and Schlag. With this statement, if we have a modulus of continuity, which is a Hölder or weak Hölder for the Lyapunov exponent, we can say the same of the integrated density of states. So I cannot review the whole. There has been a lot of work on these topics. I'm just going to mention some of the classical continuity results for Lyapunov exponents of Schrödinger co-cycles. And first, I'll talk about the random model. So the base transformation is the full Bernoulli shift. So these are results from the 80s. Furstenberg and Kiefer proved continuity in a very general setting that applies immediately here. And Émile Lepage proved Hölder continuity, again in a very general setting that is immediately applicable to this context. This is considering random models. When it comes to quasi-periodic models, so there's the torus translation on the torus of dimension 1 or higher. So I'll mention the work of Michael Gorsin and Wilhelm Schlag. The assumption in their work is that the frequency omega is Diophantine, and then that there is a lower bound on the Lyapunov exponent for a range of energies. And under this assumption, they prove Hölder continuity for one variable and weak Hölder for several variables. And this result, this paper actually is the basis for most of our work and for what I'm talking today about. In 2002, Bourgain and Svetlana proved joint continuity in the energy and the frequency. So this is the other type of problem when you look at when you allow the frequency to vary. So they prove joint continuity in energy and frequency at all points where the frequency is irrational. And this is in dimension 1, and then there is a similar result, but a much more involved proof of Bourgain for several, I said dimension, I meant the number of variables of the torus. Well, so this has been a
case of shift. The Bourgain's work is a case of shift.
Of the shift, yes.
No,
yes. That's when I say quasi-periodic, I only mean that. Yes. So this has been related to the lattice, to the integer lattice Schrödinger operator. Now, one may consider a band lattice or strip model. So instead of the integer lattice, one could take a lattice, a higher dimensional lattice, which is infinite in only one direction. So z times, say, 1L, and define an operator here, so it would act on this space, which is equivalent with, so these are square summable sequences indexed by points in this lattice, and this is equivalent with square summable sequences of vectors, where in RL, where L is the width of the strip, okay, or the band. So this is what I want to talk next. I'm going to describe what we call and other people call, we call band lattice Schrödinger operators. They are also known as strip operators or block Jacobi operators. They are also dynamically defined. So what we do, we define a similar operator on L2 of Z vectors in RL, where now the potential is a matrix-valued potential defined dynamically this way. So the base transformation is any of the examples before. Work on these types of models goes back to Kotani-Simon, Craig-Simon. For random models, for quasi-periodic models in one variable, we have results of Golshitz-Soré on positivity, of sufficient conditions on positivity of Lyapunov exponents, and Burgan-Zhytomyrskaya on Anderson localization. And I should mention that there are restrictions or certain assumptions in the models considered here. In the Golshitz-Soré case, the model considered is a constant perturbation of a diagonal. So the potential matrix is a constant perturbation of a diagonal, while in Burgan-Zhytomyrskaya it's a diagonal. So they prove localization, perturbative localization, but for a diagonal V. And we are interested in something more general. We want to introduce different types of Hopingtons here. So this leads us to the following model. We call these weights, and these weights are also dynamically defined with the same base dynamics. So these are, we have now matrix-valued weight and potential that we sampled along the orbits of the base transformation, and we get this operator. This is the transpose, and this is chosen. Sorry, this is chosen. So I lost my. This is chosen so that the matrix is the operator is self-adjoint. It was Christian actually that helped us set up this model. And there are certain natural assumptions that one should make here, that the weight and then the potential matrix are measurable and bounded. We would like to include the case when the weights or the Hopingtons are not necessarily invertible always. Because, for instance, in the quasi-periodic case, we'd like to take polynomials, trigonometric polynomials, matrices with trigonometric polynomial entries, so they are not always necessarily invertible. So then this is a condition that replaces invertibility everywhere. The determinant is not identically singular in this way. Okay, so this is a model that we want to study. And of course, you would like to study all the spectral properties of this operator, but you start with the study of Lyapunov exponents. This is the first the place to start. So we consider as before the eigenvalue equation, and we solve it formally. And what comes out of the eigenvalue equation is a much more complicated looking cocycle that has this form. Okay, if W was the identity, then it will look much more like a Schrödinger cocycle, but it's not necessarily the identity. And W is almost surely invertible, so this cocycle is defined almost surely, that's fine. And it's an 2L by 2L, so L is the width of the band. So the cocycle is going to be 2L by 2L. So it's a higher dimensional linear cocycle. And the goal is to study the analogs of the problems we discussed before, but you also have to find the correct analogs so when you talk about the positivity of Lyapunov exponent, for instance, for a Schrödinger cocycle, what would be the correct analog here in the multidimensional case? When you want to talk about continuity of the Lyapunov exponent, what do you really need? Which Lyapunov exponent should be continuous to get some meaningful conclusions? So I'm just going to mention one fact which I have only recently found, is that so suppose you want to look at to get Hölder continuity of the integrated density of states for this more general model, then you would need a Thouless formula to compare Lyapunov to relate Lyapunov exponents with the integrated density of states. For a Thouless formula for this model is available from the work of Kotani-Simon or Craig-Simon for this particular model, but for this more general one where you have arbitrary weights or hopping terms, this is a part of a paper of Jacob Chapman and Günther Stolz that has just appears. And it's exactly, the formula holds exactly under the general assumptions I had mentioned earlier here. So if we had a modulus of continuity like Hölder for the integrated density of states here, then we would be able to say the same for Lyapunov exponents. We would be able to say the same about the integrated density of states. Okay, now I'm done with the excuses for being here at this workshop, so I want to move on to something more general, to abstract linear co-cycles. All I've done was to try to convince you that instead of simply studying Schrödinger co-cycles, it's interesting to look at more general types of co-cycles. Because, for instance, the ones associated to a block-Jacobi operator are of a general kind. They are multi-dimensional and of a more complicated structure.
Didn't we convincing, didn't we?
Okay, so whether I have convinced you or not, I will move on to a more general setting. So now we consider a base ergodic system, and we consider a measurable function A that takes values from the phase space to the set of m by m matrices, and the pair PA, or the skew product map, from this bundle space to itself, defined by on the base, on the phase space we let T act, and on the fiber it's the matrix value function that acts. So this is called the linear co-cycle. It defines a new dynamical system on this bundle space. We can consider its iterates, and the iterates on the base are just the iterates of T, and on the fiber are given by non-commuting products of matrices. Okay? So in our work, the base dynamics T is usually fixed, so we identified the co-cycle with just the matrix value function A. Okay, and the goal is again to study, we have to define Lyapunov exponents and study their continuity properties. I'll begin with just a bit of linear algebra. So if you have an m by m matrix, we denote its singular values, which are the eigenvalues of G star G, of the square root of G star G. So we denote the singular values by S1, S2, S1 singular, arranged in order. So S1 is the largest, this is the smallest, and S1 is actually the norm of G. So it's the maximum expansion, and this is the minimum expansion of the matrix. And it could be zero if the matrix is not inverted. So with this definition, we can define the Lyapunov exponents by means of the Kingsman's ergodic theorem. Again, so we consider these point-wide limits, or average in X limits of these quantities. So instead of the norm, we take the kth singular value. Okay, when k is 1, this is the first singular value, so it's the norm. So this will give us the old maximal Lyapunov exponent. For other values of k, we get the next rate of expansion and so on. These quantities actually can be defined in a different way by means of the multiplicative ergodic theorem of Osseleditz, but this is a convenient way to get away with their definition in this talk. And these Lyapunov exponents, the first corresponds to the largest singular value, the second to the second largest singular value, and so on, of these iterates. So they are arranged in order from L1 to Lm, which could be, they could be minus infinity. Okay. Now I don't want to spend too much time reviewing. There has been a lot of work on continuity continuity of the Lyapunov exponents for general linear co-cycles, I will just mention that in the random and Markov case, Marcelo Viana and his collaborators Bocarnetu, Avila, Eskin, and Malieru considered this problem, and their assumption is usually the results are continuity of the Lyapunov exponents in a very general setting with no assumptions on the no irreducibility assumptions. And in the quasi-periodic case, there has been work of Svetlana with her collaborators Chris Marks, Avila, and Christian Sadel here on joint continuity of the Lyapunov exponents in the co-cycle and the frequency. And Duarte and I have been working on both on random Markov and quasi-periodic models, and our work usually has some assumptions. For instance, in the random and Markov models we assume some generic irreducibility. In the quasi-periodic case, we always assume a Diophantine condition, which is also generic, but the outputs are quantitative results, Hölder continuity or log Hölder continuity. And the method, in fact, it has a larger range of applicability, which takes me to the goal of my talk. So what we've been trying to do was to find an abstract scheme to establish continuity of Lyapunov exponents, a scheme that works for many different models. So as many of the models I mentioned in the beginning, random, Markov, quasi-periodic, and so on as possible. And so this scheme is in fact based, it has at its origin the method introduced by Michael and Wilhelm Schlag in their Hölder continuity paper. And the main assumption that this scheme requires is having some appropriate large deviation type estimates for that dynamical system. So let me say some things about large deviations. So first of all, I will remind you the classical large deviation theorem of Kramer, which is a result that so large deviations should say that tail events happen with very small probability. So if you have an IID random process and you consider the sum process, and if you make some assumptions, mild assumptions on this process, then you look at the probability that the average process differs from the mean by a certain amount. And asymptotically, this is exponentially small.
Okay, this is a very strong condition somehow. Exponential moment.
Okay.
Exponential moment.
Okay, I'll take back the mild assumptions, but an IID process. Somehow I find this to be strong because we want to do this for a dynamical system. Okay, so this is the classical large deviation theorem. Now this refers to a sum process, and now there is an equivalent statement that refers to product processes. So if you have you take the group of invertible matrices and you take a probability measure there, you take a matrix valued IID process here with this common distribution, and then you start forming products. So you look at the product process instead of the sum process before. Then there is a similar statement that if you look at the probability that this averages differ from, this is the top Lyapunov exponent of this process, differ by more than epsilon, this is also asymptotically exponentially small, this event. And there are some assumptions here that they are generic. They are the irreducibility. I'm not going to get into the detail of what this means, but these are the assumptions of Furstenberg's theory, under which you have positivity of Lyapunov exponents. They are also the kind of assumptions we make in our work, except that we don't need this one. Okay, so a similar result, by the way, holds also for Markov processes. So, and this is due to Lepage. It's from the early 90s, I believe. What I wanted to mention here regarding both this statement, the classical large deviation, and the one that refers to product processes, is that these are precise asymptotic estimates. They provide us with the rate function, which is explicit in terms of the probability distribution. So what this is saying in particular is that if you wait long enough, then this event is going to have an exponentially small probability. Now, what we need for our work, it's something which in some sense is less precise. We don't need a precise rate function here. But what we need is some measurements on the quantities that appear in the large deviation. For instance, what I said earlier was that if you wait long enough, so there is a threshold, you wait long enough, this event is going to be, its likelihood is going to be exponentially small. How long do you have to wait? We want to know this threshold more quantitatively in terms of the data. So this is one thing that we need to know. We don't need to know exactly the rate function, but we need to have some estimates on the rate function, which depend explicitly on the model. So these are the kinds of large deviation. Perhaps we should call them Chernoff bounds and not large deviations. But these are the kinds of estimates that we need for our approach. So let me describe you what we actually mean by our large deviations. So first off, there's going to be some statement on the base. So we have an ergodic dynamical system, a base, and we have an observable there, and then we take this Birkhoff sum, which is the equivalent of the sum process, right? It's a sum process. And then this is the space average. And now I'm introducing some terminology. A large LDT stands for large deviation type estimate. So an LDT parameter consists of an integer n naught, which is the moment when things start being applicable, when the process behaves according to the tail events start being very small. So we have a non-decreasing sequence epsilon n and a fast decreasing to zero sequence iota n. Think of it as being exponentially fast, going exponentially fast to zero or sub-exponentially fast. So we say that the observable satisfies a base LDT with these parameters if you look at the event that the average, this Birkhoff average differs from the space average by more than epsilon n, and the probability should be less than iota n. Okay, so this is the assumption on the base. And then we have something similar but stronger on the fiber. When I say on the fiber, I mean we take a linear cocycle now, we look at its iterates. We take the n iterates and we take the space average. And then the large deviation says that the probability that these quantities that converge to the Lyapunov exponent pointwise differ from their mean by more than epsilon n, the measure of this event is very small. And what we actually need is more than this. We need, in continuity problems, we need that this statement is uniform when we perturb the cocycle A. So by this we mean if you take a nearby cocycle, these parameters are the same. So the range of applicability of this inequality, the deviation function, the deviation function here, and the size of the tail event are preserved. Okay, so these are the main assumptions. And going back to the work of Lepage, for instance, or Bougerolles, it doesn't follow directly from their work that those parameters are constant under perturbations of the cocycle. This is not. This is not. It's not explicit, and you cannot just apply take this theorem and apply it to our case. So what we had to do was to dig in and see that the method actually allows us to get this sort of a weaker statement, because we don't care for a rate function, but this uniformity in measurements. Yes.
In this generality, what is your topology on the set of cocycles? I mean, what do you mean by close by?
Okay. Yes. Yes. I am going to say. Am I going to say? No, I'm not going to say. So in this generality, we are going to. So what we have. So now I'm going to sort of phrase the abstract theorem. So we have a base ergodic system, a space of measurable cocycles that satisfies some integrability assumptions, and this comes with the topology, and the topology should be at least as good as the L infinity, as the uniform topology. And you have to make the assumptions of this kind.
You mean the closeness of the matrices, or?
Yes. I'm talking about. So I guess the question was about what does it mean for the cocycle A of x and B of x to be close, right? What's the
You
distance?
compare the corresponding matrices, yeah?
Yes.
Just matrices which generate this cocycles.
Yes. And this should be at least as good as the L infinity distance between them. Because if you consider LP norms, for instance, then you go into a territory where the continuity of the exponents is not longer a generic property. It's actually a rare fact to get continuity of Lyapunov exponent in this kind of topology. So these are the assumptions. But these are exactly when it comes to the quasi-periodic case, that's exactly the standard topology that one takes.
But you do not necessarily assume A of x and B of x to be continuous functions or something like that.
In this level of generality, no. No.
So can you go back again to the previous slide just to see what are the conditions?
So the conditions are on the base having some weak large deviation, and on the fiber having a uniform large deviation. These are the conditions. And I should say something about this. In the quasi-periodic case, this is nothing. This is automatically satisfied because what we require, we don't require any uniformity, sorry, I got distracted. Let me phrase the pseudo-theorem and then go back to the conditions. So what we require, there are some natural integrability assumptions there, and then the basic assumptions are, on the base we have a large deviation which holds for a large enough set of observables. Okay, and this is a vague statement, that's why this is a pseudo-theorem. I'll say a few things by what I mean by a large enough set of observables. And on the fiber, we require a uniform large deviation to hold for all cocycles where there is a gap between Lyapunov exponents, which is very important that we don't need a large deviation for all cases. This is what allows us, for instance, to treat the random and Markov case, where large deviations only hold when there is a gap in the spectrum. So under these assumptions, each Lyapunov exponent is a continuous function of the cocycle, and if you have a co-cycle where there is a gap between the first and the second Lyapunov exponent, then in the neighborhood of that co-cycle, in this topology, there is a modulus of continuity. And this modulus of continuity depends, there is an explicit formula, depends on how good the large deviation is. For instance, if it's exponential, then this is going to be Hölder. If it's sub-exponential, it's with Hölder, and so on.
Should the theorem, because it was not yet proved, yeah?
No, it was proved. but
Should-
I'm not saying what the conditions are. I'm saying a large enough set of observables. I'm not saying what the natural integrability assumptions are. I'm not even saying what the topology is. That's the and actually there's more. If you there are some trivial extensions of this. If suppose you have another pattern, say you have a bunch of you have a co-cycle, and suppose the first two Lyapunov exponents are constant, are equal, and then they may be equal to a few more, okay, and then there is a gap, and then I don't care anymore. Then what this theorem implies by some trivial linear algebra is that the sum of this, so if you take L1 plus LL, this map B goes to the sum of the Lyapunov exponents is continuous with the modulus of continuity near the cocycle A, where this happens. And this is very helpful in getting continuity of the integrated density of states, because Thoules's formula in this more general situation actually refers to relates the integrated density of states with the sum of Lyapunov exponents and not just with the maximum. Okay. I wanted to say something about
the body for master.
It's too complicated. So we said that this should be satisfied for a large enough set of, this kind of estimate should hold for a large enough family of observables. In the quasi-periodic case, that large enough family could be just the continuous observable, continuous functions. And this statement is trivially true where this iota n is 0, so it holds almost surely for n0 large enough, just because Birkhoff's ergodic theorem for continuous observable holds uniformly. The convergence is uniform. So this is a weak assumption. It's a weak assumption for uniquely ergodic systems like the translation, the quasi-periodic case. But if you look at the random-based dynamics, the Bernoulli shift or Markov systems, they are not uniquely ergodic. So the convergence in Birkhoff's ergodic theorem is not uniform, and this is the replacement that we have for this. So you have a question. I should say just one thing is that important crucial in our approach is that allows us to deal with having large deviations only when there is a gap in the Lyapunov spectrum. So crucial in our approach is some type of upper semi-continuity of the maximum Lyapunov exponent. So let me say this. So I've been saying that we want to show that this quantity A goes to L1 of A, the top Lyapunov exponent is continuous. And what is trivially or very well known is that this map is, so this is known in very general situation, is that this is upper semi-continuous. Okay, so if you perturb A by B, then you are going to get this. Okay, well, it turns out that more is true. So these are limits of pointwise limits of these quantities, right? And it turns out that we don't just have upper semi-continuity, but something stronger holds a uniform upper semi-continuity, which is uniform in B and in the phase X. Now this result,
Minimality for that?
excuse me?
Don't you need minimality for that?
Exactly. So this is what I want to say is that this was a result proven by Svetlana with Rajinder Mavi that assumes that the system is minimal or uniquely ergodic. This is what's needed there. Now we want to apply it to the Bernoulli shift, for instance, to Markov systems that are not uniquely ergodic. So this will not necessarily hold. So this is true for all x's. This will not necessarily hold there, but that large deviation assumption on the base, it's enough to get this not for all phases, but for all x outside the small set of phases. So you don't get a uniform upper semi-continuity, you get a nearly uniform upper semi-continuity under a weaker assumption, which applies to random models. I wanted to say one more thing about this method. So this goes back, the proof of this is inspired by work of Alex Fuhrman, which goes back to actually a proof of the ergodic theorems by Kaznerson and Weiss, and that uses stopping time argument. And the way we obtained this in our level of generality, we went back and we modified this stopping time argument so that it applies in this situation. So this is a crucial ingredient in our inductive procedure to prove continuity. Yes.
Small set means positive measure
It
going
means
to zero, or
it's correlated to the large deviation. So small. This is.
does not mean measure zero set.
No, it doesn't mean measure zero. It means we are doing this at scale n. So small measure means of that order, iota n, which is the size of the exceptional set in the large deviation on the base.
It also goes uniformly to zero when epsilon goes to zero, or the measure of that set?
It depends on epsilon. You fix an epsilon, and then there is and this epsilon, the way you fix it is correlated with the gap between Lyapunov exponents. Yes. Not yet.
A little lower.
Okay. So now I should say that, well, I've already mentioned that this theorem is applicable to many different models, to different types of quasi-periodic models. By different types, I mean progressively more general assumptions on the co-cycle. And I'm going to give a talk next week in the workshop where I will talk about deriving large deviations for quasi-periodic, for a quasi-periodic model. It applies to Bernoulli and Markov shifts of a very general type, more general than I have mentioned there, but we have to make this irreducibility condition, which is where our work separates from that of Marcelo Viana and his collaborators. They do not make this assumption. However, our results are quantitative. So
What is the irreducibility condition?
Strong irreducibility means, so you have the general linear group. You have a measure there. You take the support of the measure. You take the subgroup generated by the support of the measure. So the irreducibility is a condition on that there isn't a finite family of subspaces that are invariant under all the elements of this subgroup.
Basically needed for the gap condition, right?
The irreducibility, you need the irreducibility to get large deviations.
To get large deviations.
Yes, for the fiber, yes, that's where it comes. And actually you need the irreducibility, really you need the irreducibility to get uniform large deviations.
And And
uniform in the co-cycle. So perhaps one could get large deviation that depend on the co-cycle, but when you perturb it, and if you don't have this irreducibility, you may lose control.
And Viana's methods are completely different. He doesn't need
Yes.
irreducibility, but he needs some conditions that you don't, some other conditions that you don't. Is that right?
They don't. First off, let me say there is I don't know a preprint of there isn't, to my knowledge, a preprint available of the work of Avila, Viana, and Eskin. But there is the 2x2 case. The 2x2 case is already written. It's in the book on Lyapunov Exponents of Viana. And if I remember correctly, the model is more restrictive to, I think it may be that the probability is the sum of the rocks. I'm not exactly sure, but I think this is an assumption. And it's not it doesn't apply, at least not yet, to Markov models. Otherwise, I would say in most respects is general, because this condition is not there, but it's also not quantitative. So the result it's a proof by contradiction. You cannot get quantitative results.
Proof of continuity.
Yes.
But you are not fully sure whether they need further conditions. Maybe it is just the artifact of writing in the book, right? Or it's not entirely clear, right?
Okay, I think I'm going to take back what's written in the book, because this can be checked. So I think in the book contains the 2x2 case. And I think the theorem may be stated in a very general situation. Now, I saw a talk of Avila where the m by m is the dimension of the co-cycle of the matrix when this is announced. And the model he took was this. So this is the probability on the group of matrices, and its continuity in these are two matrices of the Lyapunov exponents as functions of the matrices. Whether this is extendable to a more general, I don't know, because there's no preprint.
Comes here with us.
Yes. Okay. So what I wanted to say. Okay. So I meant to say that we do not cover all. The method does not apply to all the models I mentioned before. It applies to some of them, to quasi-periodic random Markov. It applies to some of those other types of base dynamics, like the skew translation, but with greater limitations. And these are known results done by Bourgain, Goldstein, Schlag, for instance. And
So what is the resulting continuity result for the skew translations?
we don't say anything new. You just consider this type of co-cycle, and the result says that if the coupling constant is large enough, depending on V, then you have continuity in the energy. However, we would be able analytic, yes, always analytic, yes.
And depending on alpha also, right?
And depending on the Diophantine condition. Yeah, no, I'm not saying, I'm just citing
Okay.
the result.
Okay,
I'm not
so
doing,
maybe there was no-
but I do have a comment here. We would be able to consider this a general context here. So just a co-cycle, a general m by m co-cycle, which is analytic, A of x and y, with this base dynamic, the skew shift. We could do this if we could only start the process, the inductive. There is an inductive process, and what's missing, it's the starting point. And that's why the starting, this works here because the procedure is perturbative, because we have this extra parameter that we can take large enough, and then we can start an inductive process to lead to the continuity. But in general, We don't have it here. We have it for the other quasi-periodic models, but here we don't know how to do it. So the method could, in theory, be applicable to the skewed translation in this generality, but there's an ingredient missing there.
It needs some large parameter, otherwise how you can do it?
To start, well, you could assume that there is a gap in the Lyapunov spectrum, or for 2x2 cocycles that the Lyapunov exponent is positive. And this could possibly say that at finite scale and for many energies you have growth. But we cannot get this in the correct form. So that's why there is a hope there. But, so I guess I will have to end by saying that what I've been talking about is forming the subject of a book we are writing on Lyapunov exponents via continuity via large deviations. It will appear next year. And we also wrote a survey that lists some of these results. And I want to end this with a picture. That this picture describes the proof, which is an inductive procedure. But I have to stop there. So.
Questions?
Just few words about what is your induction procedure you're speaking of that.
So you want to prove that a limit quantity, the Lyapunov exponent, depends continuously on the data, on the cocycle.
Okay, yeah.
So and it depends in a, say, Hölder way. So the way you do it is you start at a large enough. This is a limit quantity, the Lyapunov exponent. So it's the limit of some finite scale quantities. You start at a large enough scale, and there, because they are you use a finite product of matrices, it's easy to show that you have some sort of Lipschitz continuity at an initial finite scale. Okay, it's not always the case, but you have some kind of continuity at finite scale. Now,
Sort of multi-scale analysis.
it's a multi-scale analysis, yes. And then, as you increase the scale, you want to see that these finite scale quantities converge to the limit with a certain speed of convergence, which is uniform in the cocycle. And then this picture actually explains this. What I have here, it's N0 is the first scale, and you have some information at this scale, and you want to transfer this information at a much larger scale, N1. So this represents a product of N1 many matrices. Okay, what you do, you take this block and you divide it into smaller blocks of about this size, and the goal is to find a way to compare this long block with products of smaller blocks at this scale. And the major ingredient here in being able to do this comparison, it's the avalanche principle, which says that we can compare a product of a long block of matrices with individual blocks under certain assumptions, if some assumptions hold. So this is actually not true unless, say, they are diagonal.
You need gaps.
You need gaps, yes. So you need certain assumptions. You need a certain alignment of the singular directions. And if this happens, then you can apply this inductive procedure. And these hold inductively, and this is where the large deviation appears. The large deviation compares an average, a phase average quantity with a pointwise average. And it says that they are similar for many phases. So if you know something on average, you know it for many phases.
Okay, so we know those counterexamples to continuity by Wang and Liu for C infinity.
Yes.
Does this imply within your scheme, so we know that base dynamics is good still, right?
Yes.
So it implies that the large deviations do not hold, right?
Yes.
Does it imply that they do not hold individually, or does it imply only that the uniform do not hold?
My guess would be the uniformity is what I have not thought about it, but I would guess that it's the uniformity of the. If you have, perhaps if you have a sampling function that is very transversal, right? This is where the counterexamples come from. The fact that there are transversality parts in the cocycle in the sampling function.
Non-transversal.
Non-transversality. I meant non-transversality parts. Yes. So you take one like this. I don't know. I have not tried to prove a large deviation for this, but I would assume that if one exists when you perturb this, and you have a sampling function that is maybe less transversal with some respect, you lose the control of the large deviations. I can mention something related, which is still the analytic case, but somehow that doesn't exactly answer your question, but points towards it. So if you have an analytical cycle on the torus of the dimension, higher dimension. So we can prove continuity of the Lyapunov exponents when this is not identically singular. And this is what I'm going to talk about next week. When this is identically singular, in this case, of course, your work with Artur and Christian handles this case as well when d equals 1. But in the higher frequency case, we can still do this, but it's much, much more difficult to handle the case when the determinant is identically 0. Because once you perturb the potential, this property is not open, so you perturb it, you can have a cocycle nearby where this holds, which has a different rank, and then it's very difficult to control exactly the uniformity of the large deviations. You can get a large deviation for an individual cocycle under this assumption by reducing it to something of a lower rank, but then when you perturb it, it's possible, but through a great effort. So this is a kind of singularity which I don't know if it's in any way related to the transversality problems or non-transversality issues that appear in the C infinity case. But yeah, my guess would be this, that is the uniformity that it's an issue.
So in this abstract framework where you get continuity when you have all your assumptions, did you actually think about whether one could also in a very abstract way introduce some quantity which could classify domination?
I have not thought about this. No, I haven't thought of this. There is something else that we study in this context, which is the Osseledets spaces, the Osseledets filtration and decomposition. So actually our scheme provides a new proof of the multiplicative ergodic theorem, and also in general, and also when we have large deviations, we can show that the Osseledets filtration depends continuously on the cocycle. So that's the direction the other direction we took this work into. But I have not thought of
Since you talk about Osseledets filtration, in the singular case of these quasi-periodic cocycles, do you actually also get something that you always have a splitting? Or can you
in the completely singular case.
you generally know that, right? Anyway, so you have
Usually you assume invertibility
yes.
to get the splitting, but there are conditions under which you have a splitting even when it's not invertible. How general they can be, I don't yet know.